welcome everybody to this afternoon seminar. Zeev Rudnick will give a survey on the current state of affairs on distribution problems for the eigenfunctions of point scatterers on the torus. And this will be the sort of start of a working group that we have over at the Gatehouse for the whole week. And this will be a very informal working group with the word working underlined, so we'll discuss current problems. But we thought it's a good idea to have a more public survey lecture so that members here at the Institute get an impression on what the subject is about. So it's a great pleasure to introduce Zeev Rudnick from Tel Aviv University, and he will talk on the point scatterer on the torus.
Okay, it's a pleasure to be here again. We've been reminiscing about many times we've spent together here at the Newton Institute, but I haven't been back in 10 years, and it's changed a little bit and become even more impressive than it was before. This is a bit of an unusual talk for me. I'm used to speaking from a position of authority, and on this subject I feel most people in the audience, except for the one who just walked in, know far more about it than I do. So I'm actually welcoming all kinds of audience comments. I had a very interesting discussion with Jean-Philippe just a few hours ago about this. So what is the point scatterer about? For me and for some of the people here, it's been used as a model for a quantum system which is intermediate between systems which have chaotic classical counterparts and integrable classical counterparts. And so formally you write this point scatterer as the Laplacian coupled to a delta potential. Making sense of that requires some thinking. In the one-dimensional context, this is an old model. It first appeared, to the best of my knowledge, in solid-state physics. It was a famous model called the Kronig-Penny model from about 80 years ago. It was used to explain the appearance of electronic band structure. When I give a talk about this in Britain, I have to mention that the Baron Penny was one of the leaders of the British nuclear program, which culminated in the British atomic bomb in '52. So the Kronig-Penny model is, and the point scatterer is a useful thing if you are interested in such objects. Someone who looks remarkably similar to Penny is Dennis Hedger, and he was also involved with the point scatterer from a somewhat different perspective. So there's a bit, for a number theorist, point scatterer came up in the 70s. What happened was that there was a student in Heidelberg called Haas, who was given the task of numerically computing the eigenvalues of the hyperbolic Laplacian on the modular domain. And this list of numerical eigenvalues was circulated until it found its way to Harold Stark. And the guy took a look at it and said, I recognize some of these numbers, because those numbers are the imaginary parts of the Riemann zeros. And that made for a huge deal of excitement locally, because one dream people had of proving the Riemann hypothesis was to realize the imaginary parts, so to speak, of the eigenvalues as of the zeros as eigenvalues of a self-adjoint operator. So if you found the zeros inside the eigenspectrum of a self-adjoint operator, then you win big time. So this caused a lot of excitement until it was realized that the guy screwed up on the numerics. He allowed eigenfunctions which has a logarithmic singularity at one corner of the fundamental domain, and that was the origin of the spurious eigenvalues. So those have been understood why they appear there. It's natural to find the Riemann zeros there, but not because they come up as eigenvalues of something that you want to prove anything about. And more recently, in the late 80s and 90s, the point scatterers in 2 dimensions was suggested as a model system, as a toy model, to study things that we're interested in more realistic quantum systems. And there are 2 main problems that have been put to this model, and one is the question about local statistics of the energy levels, and the other is the fine structure of the wave functions. So what I'm going to explain briefly is what these 2 questions are and what the results are for a point scatterer, after I explain what is a point scatterer to people who don't know what it is. Okay, so the action will take place on the torus. So the torus is just a rectangle with identification of the sides. And the standard torus is when you take a square and identify the sides, and an irrational torus is when you take a rectangle with a sufficiently irrational aspect ratio and identify the sides. So topologically they are the same, but not in other senses. Now, what is the first question that we want to address? It's the question about spacings between eigenvalues. So let's forget about point scatterers. Just look at your favorite quantum system. And the remarkable discovery that was made in the 70s and 80s is that generically, in a suitable sense, there are 2 universality classes. If you take a quantum system whose classical limit is chaotic and look at the spacings between the eigenvalues of the Hamiltonian when considered on the scale of the mean spacing, you get statistics which are the same as the statistics of a suitable ensemble of random matrices. And when you look at an integrable system, which is generic in the sense that it's not a counterexample, then you get Poisson statistics for the distribution of spacing. These are empirical observations. We don't have a single proof of any of these statements. So here is the numerics. So this is, you take an irrational torus, which is sufficiently irrational, and this it's very easy to write down the eigenvalues. They're just sums of 2 squares with coefficients coming from the aspect ratio of the torus, and you plot them and you compute the distribution of spacings, and you get this thing which looks very close to an exponential distribution. I don't know how to prove this, but the picture is fairly convincing. Or you can take a billiard, so the Laplacian on a domain with Dirichlet boundary value, and if the domain is something where the classical billiard flow is chaotic, then the energy levels seem to have this kind of spacing. So in particular, there's level repulsion. And there's a theoretical curve here which comes from taking the same question for a random matrix, for the eigenvalues of a random matrix from a suitable ensemble. Okay, so these are the so-called universality conjecture for the spectrum of quantum chaotic or quantum integrable systems. So we want to take the this toy model of a point scatterer and see what the spacing distribution looks like in that case. So what is a point scatterer? It's a little complicated to explain if you haven't seen it before, so I'll take a matrix example, just a finite dimensional system. So you take a self-adjoint matrix, an n by n matrix, so it has real eigenvalues, and introduce a rank 1 perturbation by adding projection onto a one-dimensional vector space inside. So now you get a new operator, and you want to understand what is the relation between, let's say, the eigenvalues of the new operator and the eigenvalues of the old operator. And it's a simple exercise to show that the new eigenvalues are, can be computed by solving this equation. Okay, so this is a resolvent equation. So in particular, if we plot this function here as a function of lambda, so it sort of has singularities whenever you hit the old eigenvalues, and between the singularities it's monotonic, and then it jumps and then goes down, and jumps and then goes down. And if you ask it to be given to a fixed number, that number is the inverse of this coupling constant, then you're just intersecting with the fixed line, let's say this line, and the intersection points are the new eigenvalues. So that's the spectrum of the new operator. And the eigenvectors, you take the perturbing vector and apply the resolvents to it. So this is an exercise. So this is what we want to do for the Laplacian. So the only problem is that the Laplacian is not a matrix, so you have to be thinking about how to do all this rigorously. And that actually took a while to do. I think it was von Neumann who figured out one of the standard ways to do it, using his theory of self-adjoint extensions. And one way to do it is you take the Laplacian but restrict it to functions vanishing away from the scatterer. So you want to take the Laplacian and add the multiple of the delta function. The delta function is no longer a vector in L2, so you have to think about what to do. If you just imitate formally what we did for an n by n matrix and write down the resolvent, you get this series, and this series diverges. So you have to regularize it. And this is what von Neumann did. And the upshot is, I'll write down what his recipe is in a second. The upshot is that there are interesting extensions in dimensions 1, 2, and 3, but not in dimension 4 and more. In dimension 4 and more, you just get the ordinary Laplacian. So this is a low-dimensional theory. Okay, so this recipe for regularization is you put the scatterer at a given point and look at the Laplacian acting on functions which vanish near that point. That's a symmetric operator, and then you can ask for extension, self-adjoint extensions. And in 2 dimensions, there's a one-parameter family of extensions. The deficiency indices are 1 and 1. And the domains, if you fix one of these parameters, the domains are functions which look like, in 2 dimensions, like log plus a constant near the singularity. And then the eigenvalue equation that you get is more or less the old eigenvalue equation, except you have to regularize it, and this is one way of doing it. So your new eigenvalues are solutions of this secular equation. And the new eigenfunctions are applying the resolvent to your perturbing vector, except, again, it's not in the L2 space, but the L2 expansion is this thing. This makes sense in L2, but not pointwise. Okay, so again, you have as a function of lambda, you have singularities at the old eigenvalues, and in between it's monotonic, and if you fix the parameter of the self-adjoint extension, then the new eigenvalues come from intersecting this graph with a fixed horizontal line. And they interlace with the old ones. Okay, so our first goal is to try to understand the spacing between these new eigenvalues. Okay? So when I talk about spacings, I kept saying that you have to measure them on the scale of the mean. Okay? Now, let's say if you take the square torus, what the mean spacing is a subtle question. So the eigenvalues, if I scribble here, can people see it? Okay, so the Laplacian is d dx squared plus d squared dy squared. And so you want eigenfunctions of that. It looks like something like this, mx plus ny. And the corresponding eigenvalue is roughly m squared plus n squared. And for this to be periodic, you need m and n to be lattice points. Well, again, whether or not you want to put the 2 pi is a matter of taste. You have to put it somewhere. So if you forget about this 2 pi, the eigenvalues are sums of the integers, which are sums of 2 squares. And not all integers are sums of 2 squares. In fact, most integers are not sums of 2 squares. To make up for that, the ones which are on average sums of 2 squares in many ways. But what we know is that the number of sums of 2 squares up to a given x behave like x over root log x. That's a theorem of Landau from 100 years ago. So, and the consequence is that the mean distance between eigenvalues, between these perturbed eigenvalues, is growing like square root of log x. And you have to normalize by this square root of log x when you talk about the distribution of spacings. Otherwise, you get garbage. If instead of the square torus you took a rectangle with an irrational aspect ratio, then the answer is simpler. Then the var law is a standard kind of var law. Okay. So again, I remind you, in for ordinary systems, we had these 2 extreme cases: chaotic systems, which numerically, empirically have GOE distribution, and integrable systems, which have empirically a Poisson distribution for the spacings. And for the point scatterer, we try to understand which is which. And then there's a new feature that comes up. It turns out that in 2 dimensions, there are actually 2 kinds of questions you can ask about the point scatterer. And this is called the strong and weak coupling regime. So the weak coupling regime is what I've been describing until now, that you take this blue plot of the secular equation and intersect it with a fixed horizontal line and look at the intersections, those are your new eigenvalues, and those are the spacing you look at. This is called the weak coupling regime. It turns out a more interesting regime, which is called the strong coupling regime, which roughly means you shift this line upwards as you go up in the energy plane. There's a precise prescription of how to do this. Why you want to do this is a separate issue, which I haven't completely understood. Okay, so let's deal with weak coupling first. So in the weak coupling regime, we understand what's happening. Okay, so the answer is that the spacing distribution of the point scatterer in the weak coupling regime is the same as the spacing distribution for the unperturbed problem before you put the point scatterer. Which is not to say that I know what it is, because I don't know I don't know how to prove that there is a limit distribution for spacings for a torus, either irrational or rational, in fact. But if it exists, then for the point scatter in the weak coupling regime, it's the same. What does weak coupling mean? So you take a fixed self-adjoint extension. This is called weak coupling. But so if I was trying to be disingenuous, I wouldn't mumble about weak and strong coupling. I just say for a fixed self-adjoint extension, I know the truth and the whole truth. Okay, if you take
maybe a good way, the point to emphasize is that basically the formal operator that we've written down, and basically the mathematical realization that we find via the self-adjoint extension theory in the high-dimensional case, dimension 2 and 3, doesn't really give you what you originally wanted. It doesn't correspond to the case where alpha is constant, but rather to a case where alpha decays as you're in the high-frequency regime. So basically what you have to do in order to get the real thing is to compensate and do this renormalization. And that is what this strong coupling is. It kind of compensates for this weakness. Basically, the natural way for the mathematician to realize the operator is the bad way for the physicist. The physicists have realized this and said, okay.
Some physicists have realized this, I should say.
It's a physicist terminology, so one has to.
No, but most of them didn't understand it.
Well, so there's a relation. Alpha is the aspect ratio, or
it's the coupling constant. Alpha is the coupling constant.
oh, the coupling constant.
Okay.
So when you write the Laplacian plus a potential, there's this
That's what we mean.
constant, and
That's your physical problem.
okay, what is the relation between this thing and the angle? That's something that is hard to understand exactly, but at least the way some physicists have understood this, that if you want something that corresponds to putting a non-zero constant there, you have to change the boundary conditions. You have to change the self-adjoint extension as you go off the energy plane. If you take a fixed self-adjoint extension, which is maybe the natural thing to do, which is this thing of intersecting with a fixed horizontal line, then our result says that the level spacing distribution is the same as the unperturbed problem. It actually says more than that. It says that most of the time the eigenvalues don't move off very much, move off very little, in fact. Most of the time. Maybe some of the time they do. This we don't know how to answer.
Can I make a very short comment? And then to further confuse the issue, in dimension d is equal to 3, the fixed self-adjoint extension is the strong coupling. So it's really dimension dependent. So it's basically a mess.
It depends on the. So I'm just discussing 2 dimensions right now. 3 dimension is a different ballgame altogether.
In 3 dimensions, you can also choose A to be infinity, right?
In 3
You can
dimensions,
always
yeah.
choose A to be infinity.
Okay,
it's
my
a fixed
question.
one particular case.
Yeah.
But that was still, you would still call that a weak coupling.
Yeah.
No, in 3 dimensions, I don't know what
two,
weak
two.
coupling or strong coupling means.
In 2.
In 2, yeah, in 2 you could, yeah.
Coupling because the eigenvalues on average converge in the high energy limit to that. I just wanted to say one thing because Alex is here. Alex has a very similar result for bounded perturbations by bounded potentials and smooth, I guess, which also in this language would correspond to a weak coupling limit. Of course, here the difference is it's a singular perturbation, highly unbounded.
So you take a fixed bump potential, but for what system?
Torus. Take a torus.
And put in.
Determined by continuous potential.
Okay.
Torus.
And then the result is that the eigenvalues clump.
The result is that I can't make a too definite a statement, but what I say is that it is the same as without potential.
The spacing.
The distribution.
Okay, that's interesting. I didn't know about this result. So it's more or less the same.
Then basically in the strong coupling regime for the scatterer, it's not the same. That's the key thing.
Okay, wait,
That's
that's the next
We
slide.
have talked about
That's the next slide.
But in Alex's case, it's exactly the same phenomenon that most eigenvalues are close and only resident eigenvalues, go away. But
And
they
how
are
many resonant
smaller.
eigenvalues there are?
You can estimate them, but they do not contribute much.
So you know that it's lower order.
Yes, definitely.
Okay, so it's exactly the same. Okay. So again, the picture would be that in the case of a square torus, the spacing would be the same as the spacings between sums of two squares. After you normalize by the mean spacing, which is a non-trivial thing to do. And for an irrational torus, again, the same as the distribution of spacing between these weighted sums of two squares. And here you renormalize, but you don't think about it because you renormalize by a constant. And in both cases, we sort of show that the spacing is Poisson. We just don't know how to prove it. Okay, you have to learn to live with it. But we know the truth. We think we know the truth. Now, the strong coupling limit is more interesting. And therefore, we know we can prove nothing about it. So here is a picture. So this is what I can say. This is a numeric. You take the strong coupling limit and look at the distribution of normalized spacing after you unfold them properly, after you make sure that you should divide by the square root of log, not multiply. And you see this bump. In particular, you see level repulsion. You can do the same thing not just for the rational torus, which is this picture, but for an irrational torus. Okay, you see level repulsion, but the picture is not as good. This picture is about 13,000 levels near the 10 to the 10th. I'm sure one can do much more. There is no rigorous analysis of this, and even at the physical level, I don't understand what this picture is. There is a lot of discussion in the literature about it, but I cannot say I've understood it. In any case, this is a complete mystery to me, and you know, if we can prove like a tiny thing about this repulsion this week, it would be a tremendous achievement. Except I don't have any idea. So this is the issue of spacing distribution. So in the weak coupling limit, we understand it modulo what we know or what we don't know about the unperturbed case. In the strong coupling limit, I personally don't understand anything, but it looks like an interesting thing. Okay, so this is the situation. Now let's move on to discussing wave functions.
So what exactly is a strong coupling limit defined? You said that there is
Can you show the picture with the spectral equation? Because I think
Yeah.
there's a cheating way you can define
Okay,
it.
this one.
You want to put the red level so
The red level is the weak coupling limit, which means you go all the way, you fix the red, and just look at the intersections. That's the weak coupling limit. The green level is the strong coupling limit, so you move up as you move
I think
to the right.
You want to move down.
Let's first say, let's explain it first, and then we can.
Yeah.
If I remember correctly,
In
it
this
was
case,
moving
you have
up.
to move down. That's true.
So at each time you want to cross the red line with the middle point between the two.
For the weak coupling limit, you fix the red line all the way up to infinity, and look at the intersections.
So you are bending the red line so to cross each time in the middle between two vertical bars, right?
In the strong limit, no, you're not making it. Okay. The precise condition is written here. So you pick phi. So phi tells you the angle is the parameter of the self-adjoint extension. So you change the self-adjoint extension as you move to the right in this particular way. And you look at a certain window, roughly, roughly of log size in that direction. And whether it's going up or down depends on what this sign is. Okay, so it's a moving window. Now, why you pick this? So let's say Shigehara and company, the way they explain it is they compute, they make a computation of variance of where the perturbation has the most effect. Okay, and they choose that as the reason for giving this strong coupling.
Can you state it in terms of the alpha?
I cannot personally state it.
It's not an
Even
obvious.
as target?
No, you can write it down, but it's just.
No, I cannot state it. So the way they explain it, or what Henrik was trying to say, was that it corresponds to making this alpha fixed and non-zero. But I haven't understood how to actually write down an exact connection between this non-rigorous thing and this rigorous theory of von Neumann extensions.
But this alpha doesn't make any sense.
It does not make any sense
This
rigorously.
alpha is not defined.
No, but isn't... Okay, but
There
in
is
three
a-
dimension, this alpha is the scattering length, right?
So
Not, again, not in a rigorous way that I can make sense of. You understand this much better than me.
So there are
Maybe.
formulae relating alpha and phi. For instance, Bavaria has written down these formulae already in the 80s.
But the alpha, the various alpha is the scattering length, right? Or one over the scattering length.
Yeah, I think he makes a connection like that, and basically, okay, in one dimension you have a trivial, inexact relationship between alpha and phi through a boundary condition.
Right.
The problem is in dimensions 2 and 3, this relationship involves the spectral parameter itself. So the whole idea about the strong coupling limit is if you want to keep alpha fixed, that forces phi to change because you have lambda in the equation. Now Bavaria writes down these equations, but okay.
I've not been able to understand them.
Also in 3 dimensions.
Yes. And is essentially the way I would interpret it, I mean, my way of understanding is that a good way to measure the coupling strength or to define it for a pure mathematician in a rigorous way is to look simply at the boundary condition. So if you calculate your Green's function, you have a scaling in lambda, and this is somehow a term that compensates the scaling. If you don't compensate, basically you get a much weaker perturbation. And then you basically take the two constants in front of the leading term and the first correction, and you take the ratio to find that as the coupling, your new coupling constant, and then you also come out with this. This is my way of getting it.
So the bottom line for me is I could not make sense of what was written in that particular book at the mathematical level, and I don't know how to rigorously make sense of this coupling constant over there in terms of this phi parameter.
But
Certainly not in 2, but also in 3. I did not understand how to do this. In one dimension, it's perfectly understood.
So it's clear we have too many experts in the audience.
No, it's good.
I
It's
think
good.
it's a good problem. But if I can just say one thing,
Yeah, you're also an expert.
is the way I think one should just think about this is there's this variable phi, and you now look at a sequence of a family of operators parametrized by phi. And now you are fixing a spectral window that's high up, and depending on the center of the spectral window, you choose a particular realization of your family, i.e. you choose a particular phi, and that's it. And now you want to say, what do I call weak and strong coupling and so on. But you can just say, I don't care, I just look at scaling limits, and sometimes I see one answer, and sometimes I see another answer. And then when you see the answer that is identical to the unperturbed system, you can call this a weak coupling. And if you see a new phenomenon, then you can call this a strong coupling. And you need to find out what is the function that connects phi with lambda to make this new phenomenon happen. I think that's...
Jean-Philippe,
the
in
challenge.
your experience, in 3 dimensions, we were discussing this earlier, why would you think this is the right or wrong definition of...
Well, I don't
something?
exactly know what it is in 3 dimensions. What is the definition in 3 dimensions?
This I also don't understand. So apparently, if you take a fixed phi, that's a strong coupling. But why that? Again, from the point of view of computing which would give the biggest perturbation of the spectrum, already for fixed phi that happens in 3 dimensions, not in 2.
Well, I would have guessed that you put in the scattering length. That's something that has dimension of a length. The eigenvalues have dimension 1 over length squared. You ask when they're equal to each other. That's
Yeah. So this is how a physicist will do this. But
how is that this thing? Is that
yeah.
But in the case of rational coordinates, it's not the right way. Because I guess you are looking at the space of degenerate eigenvalues. You remove the degeneracy.
Yeah, you remove the degeneracies. That's right.
yes?
Can I make a pictorial explanation? So alpha is equal to 0, so no delta at all. That corresponds to the red line being infinitely far up. And if you intersect that with these blue curved lines, you've made no perturbation whatsoever. Right? And this is not obvious, but you can see already in this picture that if you set it at 0, line is at 0, things seems to have moved. You don't have very big perturbations, right? But if you move it a little bit below the x-axis, you're sort of smack in the middle. And that's this logarithmic, this log lambda term. And then if you move this horizontal line very far down, it's as if the eigenvalues come from their leftmost neighbors. So I think what the physicists said, we want lambda repulsion. Therefore, we should balance this.
Yeah, but yeah, that's what they want. But why is this the right thing to do? I have never understood. Good. So let's move back to something which turns out to be much simpler because it's independent of this weak and strong coupling business, which is the statistics of the eigenfunctions. So the motivating paradigm here is Schneermann's theorem. And Schneermann's theorem says that if you take a quantum system whose classical counterpart is chaotic in whatever sense you want, then the wave functions are uniformly distributed in phase space and in configuration space, not individually perhaps, but almost all of them in some mean sense. So the precise, a precise statement is that if you remove a density 0 subset of the spectrum, then the L2 normalized eigenfunctions converge weakly, the amplitudes converge weakly to the uniform measure. Okay, so this is how you express this formally. For integrable systems, the phase space statement is just not true. So for instance, if you take a flat torus, then let's say if you take an irrational flat torus, then the eigenfunctions are uniformly distributed in position, but they have very definite frequencies, and therefore they're highly localized in momentum space.
Yeah, everything is okay with the normalization here in this formula?
Everything is okay.
L2 norm is 1.
L2 norm is 1. The volume had better be 1.
The volume better be 1, yeah.
Or maybe this is accounted for already
No,
here.
no.
Okay, the volume had better be 1. Yeah, it's a phase space average. A computing phase space average.
Yeah.
It should be, this is okay, but it's important to make the L2 normalization 1. Okay, so this is the type of question you ask about the new eigenfunctions for the point scatterer. So again, here's the formula. You apply the resolvent to the delta function, and formally you get this series which converges in L2 in dimension 2 and 3, but not in 4. And since it converges in L2, you can normalize it to have L2 norm 1, and you can ask the question about what is the corresponding density. Okay, and then something that we now understand essentially completely is that, first of all, you have a complete analog of this Schneermann theorem, that if you remove a density 0 subsequence of the spectrum, then these eigenfunctions become uniformly distributed. So Henrik here and I carried this out for the position representation. And then I was completely misled by some numerics to thinking that this wouldn't work for the momentum representation. And it was Henrik and Kolberg here who carried it out for the phase space, for momentum as well, which is more involved, but turns out to be true. In 3 dimensions, the same thing happens, but Nadav here actually realized that at least for position representation, all of the eigenfunctions are uniformly distributed. You don't have to take away a density 0 subset.
This is only for the cube, right? For the standard, yeah.
That's right. That's right.
And this, our resultant phase space is only for the square torus.
Right. Right. I'm going to
Only more
discuss the irrational torus
Okay.
in the next slide. So for the rational torus, for the square torus, you have this complete analog of quantum ergodicity of Schnurman's theorem. The reason we started looking at it was this very appealing picture that appeared in a paper from over 10 years ago by Gregory Berkolaiko, John Keating, and Brian Wynn, where they discovered scars. So scars is the opposite of uniform distribution. It's the weak convergence of these measures to something that is very far from uniform. And Jens, with Brian Wynn and John Keating, have a theory that predicted how these curves come up. But they didn't have a theorem that actually proves it, because the theory relied on this assumption, which numerically is very justified, that the spacings between the energy levels of the irrational torus is Poisson. It relies on something weaker, but not something that's not. And just recently, a year ago, Paul and Henrik gave an argument that sidestepped this issue, relying on things that are proven, and proved that this picture actually exists. So the status is as follows. Okay, I want to say this picture. The status is as follows. As far as the behavior of wave functions is, for a square torus, you have quantum ergodicity in the sense that almost all eigenfunctions are uniformly distributed.
New eigenfunction.
Yeah, the new eigenfunctions. So,
Curved eigenfunction.
yeah, the eigenfunctions of a point scatter, the new eigenfunctions. There are old eigenfunctions as well, but they're not the interesting ones for us now. And for the irrational torus, actually almost all eigenfunctions behave the opposite way. They are scarred. That is, the densities converge weakly to something which is not the uniform measure. So it's a strange kind of in-between situation here, that actually changing the model just slightly by taking the square torus and perturbing it dramatically changes the result.
They converge weakly to, they do really converge.
No, this is weak convergence we are talking about.
Yes, I understand. But there is what, a unique limit there? Weak limit, whoever.
In the rational case, in the case of the square torus, there is a unique, okay, no, you have to subtract a zero density sequence. And then
No, irrational case.
in the irrational case, not necessarily. Right.
Morally speaking, there will be 4 deltas in momentum representation at which you have positive measures. But these angles can move around.
Yeah, so it's
No,
not a fixed thing.
So in what sense do they converge then?
Along subsequence,
Yeah.
subsequential convergence, but the main observation is that they do not, that there is not a positive density subsequence for which you see uniform distribution. That's the statement.
So maybe
Right?
if you look at this eigenfunction, just now look at the unperturbed problem on the torus. Okay, this is your wave function psi. So the absolute value is squared in position representation is 1. So that converges not just weakly, pointwise. Doesn't converge. It is the uniform measure. In momentum, it's a delta function at this point, Mn. Now, what the Mn is depends on your wave function. But, of course, you can take a sequence so that its projection onto the unit circle converges to your favorite point. And that's what's happening in this point scatter for the irrational torus. Okay. So what I've tried to just describe here is that the point scatter has these questions that you can ask about, which are relevant for more realistic systems, and in some cases you can answer them. For eigenvalue statistics, in the weak coupling limit, we understand what it is completely. In the strong coupling limit, whatever that is, we had a long discussion, we don't understand them at all. And for the eigenfunctions, we more or less understand everything now, as far as this weak convergence goes. There are other questions you can ask, but I haven't discussed them. And what is this picture? So in my apartment yesterday, I found a bunch of volumes of Physics Today. And this is the cover of one of them. So what can you see now in the quantum world? And Alice.
Alice, yes.
Yes, and Bob, it's looking spookier than ever. Good, thank you.
Are there questions?
Just curious about the momentum space. Actually, it's ZD, right? Z2. It's not compact. So how do you exactly?
No. So you have to. This is what I was mumbling about projection to the unit circle. You ask about directions. So momentum space means you work on the unit tangent or cotangent bundle and just look at the space of directions. So you take, let's say, this frequency, you look at Mn projected to the unit circle. So the action is in momentum space on the unit circle. Okay, because again, the classical dynamics here is of a billiard. So you fix, the speed is fixed once and for all. So momentum just has a direction parameter, not a speed, which is interesting.
I have actually two questions. One is just a clarification. What was the new eigenfunction?
So it turns out that in this self-adjoint perturbation, some of the eigenfunctions of the original operator remain eigenfunctions of the new one. So what happens there is that...
Even with just one scalar?
Yes. What happens is that each eigenspace is reduced by one dimension. But the let's say in the square torus, the eigenspace is actually big, so you lose one. But even in the irrational torus, there's a trivial multiplicity coming from a symmetry. So you reduce the dimension by one, you add the new eigenfunction, and that's the interesting guy. That's the Green's function. Then you have the old ones, which don't feel the scatterer. So there's nothing interesting new that you're allowed to say about them.
But what happens if you just add a potential, not this delta thing?
So this is what Jens and Alex were
But you
discussing.
didn't ask exactly the same question.
You can ask exactly the same question.
And what is known then?
So if I understood from the discussion, you proved the analog of this known new spacing distribution result, that the spacing distribution of the new problem is the same as the old problem.
Whatever it was.
Whatever it was. And you can't prove, so you know nothing here, you know nothing there, but they are the same.
They are the same. This is the only result.
Okay.
Exactly.
Do you have any result about the eigenfunctions themselves?
No.
Okay. So that, again, our methods here, so for the spacing distribution, the methods are kind of generic in the sense that they also work in negative curvature. some cases. They use trace formula, so that's soft. I consider that to be soft. For eigenfunctions, the methods are really model dependent. So I don't know if they will say, the methods won't say anything about your context, but the question makes sense, and because you can answer it here, it's conceivable you could say something by perturbing by
I'm sure something can be said. Yeah.
So that would be interesting to do.
But in situations where you could actually say something about distribution of eigenfunctions.
Of eigenfunctions.
Eigenfunctions, so in rational case. What do you know about eigenfunctions? How do they look like? I mean, are they small perturbations of fixed exponent or?
No. So, okay, here's an eigenfunction. It is what it is, right? Yeah. It's completely uniform in position, completely localized in momentum. But a typical eigenfunction is a superposition of many such guys. So this is the square root log business. The number is the number of ways of representing an integer as a sum of two squares, which is a subtle fluctuating function.
All eigenfunctions with the same energy.
Yes.
All unperturbed eigenfunctions with the same energy are somehow superimposed in the new eigenfunctions of this scatterer.
No. For the scatterer, the eigenfunction, this is what I was writing before as the Green's function. There's an exact an L2 formula.
You have an m-dimensional eigenspace, unperturbed, and you're only interested in one eigenfunction.
Yes.
Because m-1 eigenfunctions, you can choose a basis or vanish at the same.
Yeah, so here is the L2 representation.
Orthogonal to those m-1 eigenfunctions. And that's the one.
This is the new eigenfunction, so it's not, it's made of frequencies with no restriction whatsoever. There's no restriction, so it's a Green's function.
Okay.
So it's actually harder to study. Among other things, the series doesn't converge pointwise.
So in fact, you can ask this generally. How are Green's functions distributed? It doesn't have to be a particular.
Exactly.
Ask that question. How do they look like in phase space?
Or even in position. Like start with a simpler question.
Yeah. By the way, maybe one should say that in our result, in our first result, but also in the result that I proved with Per, actually our proof works generally. It doesn't make any assumption about, you don't, it's not.
There's no weak coupling, strong coupling business.
Well, it doesn't matter whether your lambda is any real number, it just matters where it lies, in which intervals. We construct a sequence of intervals actually, and within those intervals you can vary your lambda. It's not important whether it's an eigenvalue of this particular operator. This is just a special case. It works generally for Green's functions, and this actually turns out to be very useful for other things.
Any other comments or questions?
Alex?
So these point scatterers, well, in quantum mechanics, this is because it is a good model. You can compute everything explicitly. I mean,
in one dimension.
For example.
Yeah. This is Croning penny.
Problem Croning penny, that's right. For example. In 2 dimensions, you can also consider delta potentials, delta perturbations, and even the lattices of perturbations. And you can also say something explicit if you're studying. I'm not talking about these chaotic problems. I'm talking about quantum mechanical models. For example, crystal, 2-dimensional crystal, something like that. So, in other words, cynically speaking, we do this because we can't do better.
Yes,
Roughly.
It's a toy model. That's why you study it.
Here? The same here?
Yes, it's a toy model that you can try to study because we don't know how to do even we don't know how to tackle the case of the surface of negative curvature. So you look for something that's
this funny strong coupling that you. I understand that there might be some very serious, straightforward explanation why it is called strong and why it is worth studying. But looking at that, it is. You take the toy model.
Yeah, I have a comment on that.
Yeah.
No, but I didn't finish.
First, you take a toy model, and then you toy with this toy model more.
Yes. So it's not completely natural to me.
So kind of.
So the weak coupling would be the most natural thing, except that the physicists would say it doesn't give you level repulsion. We wanted to see something which has level repulsion.
Okay, well.
But Alex, from a pure mathematics point of view, you can also just say you have a one-parameter family of self-adjoint operators.
That's
You look
okay.
at the spectral projection, which is also a one-parameter family. You look at scaling limits. You couple these two, and you want to make a statement about.
So you
spacing
have essentially few parameters and you want to study asymptotics and as parameters go to infinity or don't go to infinity together. They do something together. I understand.
So I think there's one reason why it's quite interesting, because this alpha parameter, or whatever you want to call it, you can numerically interpolate between Poisson level repulsion, that is no level repulsion, to something that's halfway to random matrix theory. So somehow a one parameter family that gives you Poisson in one end and then something random matrix like in the other.
Right.
And it's a parameterized family. But
Yeah, so the way a physicist would describe this picture that I have here,
Mhm.
so this is called the mermaid distribution.
This is
Mermaid,
mermaid distribution.
the little mermaid. Why? Because it has a Wigner head. I mean, Wigner is random matrix theory. And a Poisson tail.
Poisson tail, okay. This is so subtle.
No, I kid you not. This is, if you read the literature, the physics literature, the PRLs or PhysRev, this is what it's called. So they tried, they meaning people who are very clever, some of them are good friends of mine, they tried to model this distribution because we don't understand what it is. Oh, sorry, I don't understand what it is. And one suggestion was to take a Poisson sequence and sort of remove every second level. And okay, so if you ask someone like Omer Angel here, he can compute this instantly, what the spacing is, and you get something which has level repulsion. But what it has to do with the original problem, we don't understand. And when you look at the numerics, it's not exactly the same, but it has this feature of Poisson tail and the Wigner head. This thing has the same feature. Now, we don't understand if there is a limiting distribution here. Even that we don't understand. And if there is a limiting distribution, what it is, we also don't understand. But at least it's some interesting pictures.
Well, about these two limits, so weak limit and strong limit. So weak limit is one way of how phi depends on lambda, right? And
Weak limit is that phi is fixed.
Yeah, but you can call it why.
Yes, yeah, it is a dependence on
Strong
lambda.
limit is some different dependence on
Yes.
lambda. Have you tried to look at something in between? Maybe there could be some other limits other than Poisson and.
So again, as far as proving anything, we can only prove something in the weak limit, in this one fixed. As for spacing, for eigenfunctions, we know much more. And no, we haven't tried.
But I thought you also consider limits where you are making phi lambda dependent and where you can get a spacing distribution that still remains Poisson. So essentially there are two answers.
Because if you take something phi constant or take it to be weakly constant, the methods work the same way. So there's so once you realize there are two limits, you try to see if your proof works when you shift phi with lambda, which is what we did. And if you shift it a little bit with lambda, but not in this drastic way, which is a strong coupling limit, it still works.
But in drastic, but not quite as drastic.
Yes.
It's still.
Yeah, it still works.
I mean, if you let it wiggle completely crazy, then you can get any spacings
Well,
you like. So
obviously,
it's
Yeah, if you sort of
interesting. Or
okay, this is for people who've gone to the army. If you're not so good at target practice, you first shoot, and then you draw the circles.
Yeah, you know this is recorded and we don't
Ah, I see.
any state secrets.
What about several scatterers?
Okay, so that's a question that yesterday at dinner we realized, I think Para pointed out. Actually, we don't know anything. We haven't looked at it. Two scatterers.
Well, I'm
Okay.
looking at it now, and this is actually interesting for different reasons. So first of all, I mean, the complete theory applies as well. You can use self-adjoint extent theory.
Yeah, this
You just have a
theory
rank
exists.
n perturbation. Everything is known. But the eigenfunctions are much more complicated because you get superpositions of Green's functions, and the complexity is in the superposition vector. You have some complicated, you have to calculate the kernel of some matrix, and it's very interesting actually. So I'm looking at that in the context of random Schrödinger operators. So you randomize the positions and couplings of your guys, and then the fact that you have explicit eigenfunctions and the complexity lies only in the superposition vector. This puts you in a much better situation than for, let's say, more generic random Schrödinger operators with smooth potentials. Because another good property of the point scatterer is that in a certain energy regime where let's say you take a smooth compactly supported potential and the support is smaller, let's say, than the wavelength, in this regime you can approximate actually. You can approximate generic random Schrödinger operators, and the fact that you can use number theory here to study these point scatterers makes them actually very attractive models compared with other models that people, let's say, in disordered systems have studied. So that's actually very interesting to take a lot of scatterers and study different regimes, different limits.
I think even 2 scatterers would
But
be
when you say
interesting.
the 2 scatterers, the strong coupling regime, do you then also want to sort of scale the separation?
So it may be that, so we haven't thought about the problem at all. Here, so if you notice, I didn't really care where the scatterer was. It's a peculiarity of the torus which has a lot of symmetries. Maybe with 2 it will come in, or maybe not. I don't know.
Things become much more complicated, that's for sure.
All right, thank you all very much for contributing to this. Most of all to Zeev Rudnick for a great lecture.
Thank you.